So, welcome to the talk with the longest title of today, which is JChem PostgreSQL Cartridge, handling large volumes of data, of chemical data, in a scalable way and on a tight budget. I can say that in one sentence. Incredible, isn't it? So, let's take a step back. Why use database in the first place? You can handle data in many ways. Well, let's make a little list of things that pop to mind. Data consistency. If you have everything centralized, you can keep your data consistent and interlinked without the risk of overwriting somebody else's work, for example. You can secure it and you can make it safe so that not the wrong people can access it. That is a lot easier to do in a database environment than, for example, when sending spreadsheets to other people by email. Central storage also makes it easy to back up your data so that you can lose everything when the whole server park go on fire, for example. And of course there's speed. And today I am going to concentrate only on speed. Speed is only important if you have to repeat this task several times. So if you have to do one search, don't bother with the database. You can just as well load it up in KNIME and do it in KNIME and go and have coffee. There are more reasons why to use a database. One of them is the very nice feature that you can centralize all your tools and all your licensing. That's more of a convenience thing, but I'm going to concentrate only on speed. I cut this talk up in 3 parts. This was the general part, and if during any of the parts where it is consecutively getting more technical, you feel the need to take a toilet break or anything, feel free. It is going to go into the nitty-gritty. So, why the PostgreSQL Cartridge? If you have your data stored, you can store it in many ways. I've listed a short number of them. There are more. For example, I have not listed Derby database, which I not really consider a real database because you cannot use it in a multi-user environment, or for example, Microsoft SQL Server or anything. For me, the 4 main ways of storing data are these 4. Text files, MySQL database, which is just a big bucket because it has no intelligence whatsoever. And then there is PostgreSQL and Oracle. Let's have a look at the landscape. This is Holland. Joke. So, what are we going to do? We want to integrate it with tools. If you store your data as an SDF, you can easily load it up in a number of tools. For example, the little icon on the bottom is Reactor, one of my favorite ChemAxon tools, or you can load it up in KNIME, or you can use the kinky Padel nodes from the University of Singapore, which calculate 1800 descriptors if you have ever a need for that. It's really cool. From files, that goes really easy. From a database, it usually takes a bit of extra work to get things running. So that's why the green smile with files. But then, of course, you're going to have search. On the bottom, I don't know if you can read it, I put a bit of SQL that is directly in a big testing table that I made. And here I'm searching on a scalar value, the molecular weight. And on the bottom, you see the performance. It returned 10,000 rows, and it did that in 4 milliseconds. I cannot blink my eyes that fast. That's quite impressive. Now, on a file, of course, that does not work. And on any database, it works like a charm. But then it becomes difficult. You want to do a chemical expression search. And being a SQL guy, I write SQL. I don't go into a tool and do it with clickety-click. So in the cartridge, you can do something really cool. And that is you can integrate SQL expressions you can integrate chemical expressions into your SQL. So here I do a substructure search where there is a nitrogen double bond in it. Excuse my lack of chemical knowledge. I know this, and that's about it. I'm a real IT guy. In MySQL, that does not exist. You have to load all your data into a tool from the MySQL database and do your chemical searches in there. In the Postgres database, this works with the ChemAxon cartridge, and of course in Oracle it also works. So that leaves us with a choice between the last two if you want to have some real speed and some real flexibility of doing chemistry in your database. So that comes to the last choosing point, and that is the cost. Now, files don't cost anything, MySQL doesn't cost anything. Postgres, actually the database is free, but the cartridge is not. And Oracle is, well, quite the opposite from free. And since this picture is a nightmare to me, for me, the choice was obvious. So, there are still some issues with this. The cartridge is not completely mature yet. I have found several bugs over the last year, working together with the people of ChemAxon, and so far fixing most of them. But yeah, it's not completely bug-free yet. You might discover funny things, and if you have a lot of people relying on the database, then finding bugs might not be your hobby, and you might want to go for the expensive but reliable version. Some other issues are mixing chemical and non-chemical clauses may need some twiddling to get it really perform very well. Otherwise, it might be that your database decides to do a full table scan on the chemical expressions, and that is a nightmare. Mixing several chemical clauses, it can be difficult, and most and foremost, the last one, the not operator cannot be used with a chemindex. That means you cannot say something like where the compound does not include substructure something. That really does not work, and you need to work around it. When we were at the point of deciding, shall we use Postgres? I was thinking, we should just test it with something mad. And we devised a mad plan, and it was to run reactor on a subset, well, I call it a subset, but actually it's everything, all commercially available compounds. And we used the Grignard reaction. So the first question occurs again, why pump it through a database? You can just feed it to a reactor. Should work. Well, no, it won't. In the library that I compiled of commercially available compounds, and this is a bit of a sloppy library. I mean, it's not really deduplicated on salt forms and things like that. Doesn't matter. It's about 12 million compounds. If you feed that to the Grignard reaction, it has two reactants. So that would lead to, I cannot pronounce that number, 144,000 billion combinations. Big number. It would take a fast computer a considerable amount of time to try that. I'm not going to try. So you can pre-filter your data so that you only feed the correct data to reactor. Furthermore, you can organize your data. You can cluster it on whatever you like, for example, per vendor, per chemical type, or just segment it on fixed chunks to distribute your workload. Because you can use reactor in a distributed way by running it on multiple computers. And something I found out along the go, in reactor, there are already filters. And they use chemical expressions. They use include expressions to say, you need everything that contains, I don't know, a ring. And they use exclude expressions. We don't want nitril. But they are not always correct, not entirely. And if you pre-filter everything, you can correct these little mistakes, if you find them, without touching anything in reactor. That's actually really powerful. And the last real advantage that I found is that it's really easy to test and fix. So you run a subset through your reactor with all your pre-filters in place, and then you find out that you missed something. You just go back into the expressions that you built in the database, and you try again. And it goes really quickly. So, to really make this work, we first had to gather, curate, and store a lot of compounds in the database. and then we query them, and then we feed it to reactor, and then in gray is the boring part, collecting and using the result. I'm not going into that details, because we didn't finish it actually. This is a map of all the vendors that I found about 2 years ago, and as you can see, there are quite a lot of compounds available. A lot of them overlap. There's one very funny one. I don't know if there's anyone from Aurora Fine Chemicals in the audience. I hope not, because they refuse to cooperate. That's why they are in light color on the bottom. Nobody has any idea how many compounds they actually have. Because one recurring theme, and that is really comical, is that all these vendors, almost all of these vendors, actually lie. They always say, we have 20 million compounds. No, you don't. So, getting it into the database. There is a very easy way to get SDF files into a database, and that is the first SQL statement on the top. But it has a little problem. It actually loads the entire file, the SDF file, directly into a variable in the database's memory. And as soon as you hit about 100,000, 200,000, you'll start to run out of memory. Now you can expand the memory and have it more memory for variables instead of optimizing your database, but eventually you'll run out again. So that was not really working very well. Then we tried through KNIME, and sorry John, but at that time KNIME was really bloody slow. So that's why the snail, that was not really working very well either. So then we turned to using the old tool, JChem, and that worked. You had to first prepare the tables from the GUI, just make a table, say what type it is, and then do some command line fiddling with the A command to add the data. And it just rams it in. It goes really quickly. Then you do some SQL to convert the types into a local cartridge internal format, and you create the index. And that is where the magic happens. This index, I have no idea what it actually does. People of ChemAxon will know very well, but they won't probably tell it. And that is what makes searching really fast. And the good news is, actually, it's really, really efficiently using the resources that you throw at it. This is a top command on my server, and as you can see from the enormous amount of red, that is the CPU utilization of every core. It's using almost 100% of all resources during this index generation, which took about 40 minutes. And after that, everything is indexed, everything runs like a charm. So, pre-filtering. This is the Grignard reaction, and just a quick reminder, we pre-filter because we don't want to have n² performance, which is horrible. And to pre-filter it, you basically have to say, we want to keep everything that applies to this template, except, and then comes a large list of, well, let's say junk. It's not so easy as it looks, actually. For the reagent, it's very easy. You just have to conform to the template. That's the top SQL query. Yeah, it's just a smarts query, and you get 125 hits, and those are your compounds. But the other one is more difficult. I just tried with only one exclusion, and there's a knot in it. Doesn't work. Actually, it does work, but it starts to do everything one by one through the database. So after 40 minutes or so, I decided to just cancel the statement. Not a good idea, not going to work that way. So I got a little trick. This is where it gets technical. Let me describe this in a metaphor. You take a big bucket, you throw in everything that you want, and then you scoop out all the garbage, one by one. That is what I did. So I create a temporary table, I throw in everything that adheres to the first clause, which is a carbon double bonded to an oxygen, and then I delete from that temporary table everything that has a nitrile, everything that has one of these free hydrogens connected to a nitrogen, etc., etc., etc. And after all these queries, which take between 1 and 2 minutes each, you end up with a complete set. Beautiful, it works. Not super fast, but that's not the point. Then there appeared to be another way to do this, and that is with the except operator. In SQL, you have, for example, the join, which is equal to the logic AND operator. So when it's in table A and in table B, you let it through. You have the union operator, which is the OR operator, and you also have the except operator. So it should be in table A, except it should not be in table B. Except that failed after adding more than one except. What a nice sentence. I heard that they fixed this, luckily, because it did not just fail to run, it actually brought the database in a deadlock situation where you had to restart the whole database. Oops. So we didn't use that. Then procedure starts to become really simple. You just export what you found. In this case, it's a join from the temporary table with the real compounds table. And you can make it into an SDF file. I prefer SDF over other file types because you can add information like your IDs, your fingerprints, whatever you want. That is all very easy to automate from any database, but also from Postgres. And then we needed to feed it to reactor, run, and do something with the results, but I'm not going to show that. The conclusion is, yes, it works. And that is exactly why I started this test case in the first place. So, handling large volumes of chemical data in a scalable way and on a tight budget is possible with the PostgreSQL Cartridge. And that was it. Thank you to all the people of ChemAxon and some others that helped me to get here in the first place.
Thank you, Ellert. Any questions?
Not a question. That was a really super talk.
Thank you.
The only thing that was wrong with it is the title's more than 140 characters, I think. We'll abbreviate it.
I'm sorry, it's interesting really talk, but I not really get the point. Why you should do this selection using a database? Why you cannot make a selection of necessary reagent just based on one file from using KNIME or any Java, whatever?
You could, absolutely. But this was a test case. I mean, it was just one reaction. But there are many, many more reactions that could be tried.
So final purpose was to make this in general automatically selection some reagent for some reaction.
The test case was just to see if the database can handle such large volumes in a bit of a quick way. And this was a suitable candidate.
I have to acknowledge that the import for the database is not so nice as you would expect for the JChem. But actually, it's just on the command line we have the limitation what you have mentioned, but we have to document it that it can be easily overcome with cutting the SDF file into chunks and then just load it one after the other from a shell script. I think this is it's a documentation issue that we should improve, and also probably later on we create a nicer import module, maybe a GUI one. And the other one, which I would like to reflect, is that
being a command line guy, I mean, I'm a real
you're right.
Linux nerd.
Yeah.
I prefer command line, but if you could improve the import process and automatically chunk it, that would be fantastic.
Yeah, actually it's the limitation of not us, but it's the PSQL client which has the memory limit. And the other one is thanks for the bug report. We have fixed it.